So today we want to talk about non-ideal gases. The gas laws that we've been dealing with so far have applied specifically to ideal gases. However, in reality, there's no such thing as an ideal gas, which I'm sure begs the question, why are we using gas laws for ideal gases if there's no such thing as an ideal gas? Well, when you have room temperature, approximately room temperature, and pressures that are at or below 1 atmosphere, or pretty close to that, the gas laws are really good. They're really successful in predicting gas behavior. However, these are the conditions that are a problem. When you get to very low temperatures and you get to high pressures, very high pressures, there are serious problems and deviations in values you get from the ideal gas law. Um, and those that you observe under experimental conditions. So what are the problems? Well, the first contradiction is dealing with the assumption from the kinetic gas law or kinetic theory that gas molecules occupy a negligibly small volume relative to the volume of the container. Okay, what the heck does that mean? It means that the entire container is assumed to be completely free volume, that the gas molecules don't occupy any of that volume. Well, the reality is free volumes are less than predicted because the molecules do take up some space. And it's particularly noticeable when you get to those low temperatures and high pressures. So you can't just assume when you get to those low temperatures and high pressures that you're all free volume in that container. The gas particle size does matter. The second contradiction is that according to the kinetic theory, gas molecules have perfectly elastic collisions. In other words, there's really no intermolecular force of attraction between those molecules. Well, in reality, you do have interactions between the molecules when they collide. Now, if you're at normal temperatures and pressures, that's not really observable. Well, it's pretty negligible. However, when you get to those low temperatures and high pressures, the molecules, when they start moving more slowly and sticking together somewhat, I guess you could say kind of simplistically, because of those intermolecular attractive forces, they're going to collide less often with the container walls. So you're going to get gas pressures that are lower than you would have predicted under those conditions. So how do we correct for that? Well, we use something called the van der Waals equation. Van der Waals equation on the right-hand side looks just like our normal pervert equation, PV equals nRT. The nRT part doesn't change. We've still got temperature in kelvins. We're still dealing with the ideal gas law constant, still dealing with the number of moles of particles involved. However, pressure and volume do change. And we have to add a correction factor in order to really be able to tell what's actually going to happen with those pressure and volume values. As you notice in this equation, we're adding a correction value to the pressure, and that correction value deals with the number of particles in the volume. It deals with something called A, whereas whenever we correct for volume over here, ending up with less than free space than we thought we would have, then we've got a factor known as B that's also taken into account. Now, where do we come up with these values? Well, there's a table of van der Waals constants, and that table, and it's just a few here that you see that'll be in your notes, but it lists the A and the B values for a few of the elements, and those are the ones that you're going to use if you're asked to calculate something using van der Waals equation. Now, honestly, I haven't ever seen them actually ask us to calculate using van der Waals equation, but we do have to understand it conceptually. So for me, the best way to understand it conceptually is to at least have done a couple of calculations with it. So look at the example. It says using both the ideal gas law equation and van der Waals equation, calculate the pressure expected for 10 moles of helium gas in a 1-liter container at negative 22 degrees Celsius. Well, let's do just our normal pervert equation first. Assuming that everything is good as far as our intermolecular attractive forces, as far as our free volume, we're going to go with the kinetic gas theory. So Looking for pressure, we're going to solve pressure as being nRT over P over V, excuse me. And it says we have 10 moles of the gas. I'm going to extend this a little bit so I have a little more room to work with. But we have 10 moles of the gas that our R value, as usual, is 0.0821 liter atmospheres per mole Kelvin, latomolts. And it says our temperature is negative 22 degrees. So add that to 273 and we get a temperature value of 251 kelvins. I'm going to divide that by the volume they give us, which is 1 liter. And we end up with an ideal gas pressure of 206 atmospheres. That looks kind of like 266. Let's change that real quick. 206 atmospheres of pressure. Now you can see that we are under a great deal of pressure here, 206 times the value for atmospheric pressure at sea level. So this is a very high pressure situation. So we could assume at this point that we probably are going to see a big deviation between what we would expect for an ideal gas and what we really see experimentally for a real gas. So let's look at van der Waals equation now. Myself a little bit more room to work again. And van der Waals equation is that pressure with the added correction factor times the volume with its correction factor is equal to nRT. So the nRT side is going to stay the same. If we look on the next page in the notes, you'll see that the A value for helium gas is 0.34. I'm not going to put in all the units. There's a lot of units on that, but I'm not going to muddy the waters with so many units right now. So 10 moles. The volume is 1 liter. I'm going to square that. The volume, 1 liter again. The B value for helium on the next page is 0.0237 times the 10 moles again. And we're still going to be equal to nRT, 10 moles. I'm going to run out of room if I'm not careful. 0.0821 latomolts. And I'm going to squeeze in the 251 kelvins here. Okay, so that's the equation. Now let's solve that. We end up with P, keep your brackets in, remember, P plus, and when we work out all that correction factor, we end up with P plus 3.4. And we work out the next correction factor, and it's 0.763. And that's going to equal our 206 that we saw in the previous problem. But now with those correction factors involved, once we solve for P, we end up with the fact that P is equal to 267 atmospheres. So you can see that with the extra pressure and with that added discussion of the difference in a real gas and an ideal gas, you're going to get a significant difference in the pressure values that we would see experimentally compared to those that we would calculate for an ideal gas.